Okay, so last time we discussed this AND realization, and we discussed the complete details of how we obtained W1 and W2 in specifically for this AND gate, and we came to the point when we discussed everything that the W1 and W2 and W3 are 20 and the bias was minus 30. So this is what we obtained. And two important points that we uh, concluded from this analysis was that the need of bias is important because you cannot avoid bias because constraint 1 was not fulfilled, which is here. This constraint was not fulfilled, so the need of bias is important. And the second thing is no unique value of W is possible. So you can come up with some other values also. So that is also possible until unless you satisfy the constraint that is required. So as you obtained this W1, W2 and bias B as minus 30, so you just plug it into the equation that we had, then what you will get is 20xi plus 20xi2 minus 30. So it will be your equation of the straight line. And once you normalize it, what you will get is x1i plus x2i minus 1.5 equal to 0. So this is your equation of the line. And if you plot this line, then you will observe that it will separate the 4 points which are given over here. So you can see this will be your 1.5, and this will be your again 1.5. So you can see how this line is separating the 4 points which are over here. It's a straight line with a negative slope of 1. So this finishes off with the AND realization. So let us take one more example to get completely confident about what is going on here. So the second example that I am taking is OR function. So by seeing the table over here, what you can observe is the OR function actually behaves like if you have two inputs, 0 0 it will be 0. If you have 1 0 it will be 1, 0 1, 1, 1 1 and 1. So except 0 0, rest of the all inputs will be all the outputs will be 1. So as discussed last time also, and you can see here also is like this factor w1 x1 plus w2 xi. So please note I am not taking bias here. So if bias is not there, then it will be w1 x1i and x2i. So this is basically zi, z11. So what is the polarity of z11, which is over here? We discussed it last time also. So when your output, which is y hat, if it is 0, then it means your Z11 will be negative here. And if the output is 1, then your Z11 will be positive. And if your output is 1 again here, then it will be again positive, and same for this case as you have it for here. So let us plot the diagram for OR gate here. As you can see, so in case of OR gate, we have data plots plotted in this fashion. So we have, for the output 1, we have 3 points which are having a value of 1 like this. And the fourth point that is having a value of 0 is this one, which is 0 0. So by observing these points, you will immediately come to know that since we are dealing with a single node perceptron or a single class perceptron, then you know that the perceptron is a straight line. When you write the equation of a perceptron, it's a straight line. As it's y is equal to w transpose x plus b. This is the equation of a straight line. So you know that by clearly observing this figure, that this line will be this one. So this can move this side or this side till we are properly able to classify the two data points, that is 1 and 0. So it can move this side also and it can move this side also until unless it's unable to classify one of them. So that is the margin actually. So you have a margin up to this point, up to this. So So to carry out this process, again we are considering the first case, which is this one. This is the first case, and in this case, what I am saying is, W1 x1 plus W2 x2, and what we are saying is we are putting the value of 0 over here. So once we put the value of 0 over here, then you again see that the summation of the two is giving you negative, but it's not possible because both the inputs are 0. So again, it comes to a point that without the bias, this neural network also cannot work. So, so for that, what you do is you keep the value of minus 30. So once you keep the value of minus 30 here, then you know that you will satisfy this constraint, which is given over here. So once this is done, so this actually ensures, the first case is telling you that bias is important and it has to be added to the this equation. So, so now as we have selected bias as minus 30, what we do is we do the second case. And in the second case, what is there? In the second case, x1 I is 1, x xi2 is 0. So in this case, what will be the equation? It will be w1 minus 30 and it has to be positive. So if that is the case, what you want to do, how will you achieve this constraint? You will achieve this constraint by putting W1 as 60. So anything can work out. You can put 40 also, but we have to see when we will come to the other constraints. So W1 is equal to 60 for now is satisfying this constraint. So we will select W1 as 60. Third case. In the third case, the first feature vector is 0, the second feature vector is 1. So again, the same thing as that of the case 2. So in this case also, what I am doing is I am taking it as 60. So this is the third case. In the fourth case, which is important, where we have both the weights and we want it to be positive. So if we want this to be positive, you can see over here, this set is, and we are taking W1 and W2 individually as 60, then we are satisfying this. But if you would, so the constraint of W1 plus W2 to be greater than 30 plus some positive delta. So you have to actually satisfy this constraint, which is important. Are you guys able to hear me?
Yes.
Okay, fine. Okay, so this constraint is important. So as we have taken 60, so it will always be greater than this. So now, but any W's that you want to take has to, within this constraint. So now, as a result of which, you have this two W1 and W2 taken as 60. The third one is taken as minus 30, as we have just derived by using all these cases. So once that is done, you can plug in it to the value of y hat, which is this one. And now when you keep the individual values of xi's, you will get sigma as minus 30 here. In this case, you will get sigma as plus 30. In this case, plus 30, and then in this case, plus 90. So when this is the case, we have already discussed, for this case, the output will be 0. For this case, output will be 1. This case, 1, and this will be also 1. So as you can see from the truth table now, that it's basically realizing an OR gate. So this is the neural network that corresponds to the OR gate. So now we have seen that a single node, because we are dealing with only one hidden node here, one node in a hidden layer. So it's also called as single layer perceptron. So this one is basically classifying two classes, either 0 or 1. So you can do that same exercise for not function also. I will not be doing, but this is for you, and then you can realize that the weights that will be coming for this NOT gate will be plus 10 and minus 20. But uh, you can take any other also, depending upon your constraints that you will be obtaining here. So this is for you as an exercise. Okay, so the capacity of this perceptron that we have discussed just now can be observed in this fashion also. It's a 3D diagram which you are observing here. The y-axis here is basically the sigma or a non-linearity that we are observing, like because we have this sigma times w1i plus wi2 minus bias. So basically it's a complex function of w1, w2 and b. So y-axis which is showing over here is actually sigma. It can be, it's a earlier it was represented as g, which means any non-linearity, whether it's a sigmoid or tan hyperbolic, it depends. So it is showing you a block diagram, or it's showing you a 3D diagram of this, and you can see that these values which are given over here as a red dot, as a round, is it's lying in this region, and the crosses are lying in this region. So you can see how easily a single node perceptron can classify two classes. And this wall which you are seeing over here, the one which is having a brick wall over here, right? This brick wall can, can move this side or this side depending upon the bias. So it's a 3D version of what we are seeing here as a 2D version. So if you project it onto the 2D space, if you project these points onto the 2D space, you will get something like this, and it's a simple case that we have already discussed. And this, it's a special case of, you know multiple data. So for example, here we have only four data, but there can be a situation where we have multiple data. So in that case, what will happen? You have x like this. Since we are taking here four inputs, that's why we had this four inputs here for the particular gate. But for here, if you want to consider this as a generalized version, then you will have these multiple inputs also along with this x. And for this, you will have multiple these inputs. So again, you can easily achieve this type of classification using a single node perceptron, where these two classes are can be easily separated by using a linear boundary. So all these and or gates are a special case of all these two class classifier where we have multiple inputs. Okay, so this is the capacity of the perceptron. By capacity of the perceptron means what is the limit of this perceptron, what kind of problems it can address. So these are the type of problems that it can address. So now what we will do is we will discuss multi-class perceptron. And in multi-class perceptron, what we will do in the earlier case, what we were doing, we were only considering this node as the first node, and we were discussing all the analysis based on this node. But now I am adding a complexity here by adding one more node in this single hidden layer. So this is the first hidden layer. But now we have two nodes. This is the first node, this is the second node. And these blue lines which are showing over here are actually the earlier weights that we had already discussed. And this bias B1 shown by blue line is the earlier bias that we had already discussed in our last lecture. And the new weights which are coming because of this addition of new node is given over here. And now you can see the convention. The convention for the weights was that, this is the layer at which you are working. So this is the single hit, this is the first layer, so that's why it's W1. And then we had from and to. So it's moving from 1 to second node. So all this will be 2 now, because you are moving from first to the second node which is given over here. So that's why it's all 1 2 2 2 3 2 4 2 and n2. So here we are considering n inputs, n features of a particular example I. So this is a addition of second node in first hidden layer, and now the output here will also be y2 hat. Earlier it was y1 hat. So this was able to classify only 0 and 1, but now we have multi-class classification going on. So now you have y1 and y2. So that's why we also call as multi-class classification, multi-class perceptron for this case. So generalizing this from what we have derived earlier, as you may recall from your last lecture, this equation we have already derived and understood in details from our last lecture. So this is for node 1 as discussed as given over here. So this is for node 1. So we can actually write it for node 2 also in a similar way as we have done it for node 1. So the only difference will be indicated in highlighted section. So what is the highlighted then? Highlighted pink section is this one. So you can see that this is the only difference in indexing. So why we are writing 2 here? We are writing 2 here because it's second node in the first hidden layer. And this W which is given over here is written like this as a matrix form. And again you can see how this W is actually propagated in terms of the convention. So it's going in the end of this indexing. Okay, so now you remember one thing, you have now two nodes. This is Z11 and this is Z12 which is coming because of the two nodes you are taking in the hidden layer. So now if I generalize this to P hidden nodes, so actually now we are increasing it to P nodes. So in that case it is simple. What you do is you actually connect the two together here. This one, this one, this one, this one. So everything will be like up till P nodes, it will be like this. So we are generalizing this equation till P. So this is also easy, right? So this is the first equation that we discussed. This is the second, and this is up to P nodes. So now the important thing is we want to combine all this. So whatever is there, we want to combine it and make it as a single equation. Remember that I wanted to implement this in a form of vectorization. Vectorization is actually making how to make your code fast by using matrix multiplications and additions instead of writing them in this fashion, because this requires for loop from running from I equal to 1 to p, but I don't want that. I want a matrix implementation of this complete set of equations. So how we can do that? We can do that easily by writing this. So now you can see I am writing this again some hypothetical z symbol like this, and then w that we have already discussed like this. This is your x, this is your bias b, this is the capital B. And here you note that the samples x are now n and m. So we have n features and m examples. In case of W1, the matrix will be of size P hidden nodes now. So this is P. So this is changing now. Earlier this P and this P were 1. Now since we have generalized it to P nodes, so this P is coming because of that. This is features and this is examples. So now I also call this as double vectorization. We will see what is this. So I call this particular expression as double vectorization because of the reason which is shown over here. So you can see that the new Z1 which I am defining over here is actually the original Z1s like this, and it will run up to P hidden nodes, and its individual Z11 which is given over here is basically represented as a 1D vector like this, which is this one. So it can be represented like this. Z2 is represented like this. So you can see now how vectorization is coming here in two steps. The first step is you are writing this particular vector as this, and in this within this vector, each of these individual elements are represented as this. So one vectorization is happening at this step, and the second vectorization is happening at this step. That's why I'm calling it as double vectorization. So same for this ZP also, and you can see we have here, and the dimension of this matrix is P, because you have P nodes and M examples. So that's why the dimension of this matrix is P cross M. So let's discuss the dimension of W. So the dimension of W matrix is this one. Please note that in earlier case when we discussed in a very simplistic form, these W's were not there. These W's were not there. It was only this one. But now, because we are considering P nodes, so everything will come here. So every W1 will come here. So for each W's, you will have some uh, vectors corresponding to that. So this bold one W1 will have this vector, this W2 will have this vector, and this WP will have this vector. And you can see again the dimension of this will be that it has P nodes and N features. So this is basically this color is showing you features and the green one is showing you the number of nodes. So this is the dimension of W. Same with the B's, as you can see over here. And again, from this also it's evident that B will have P hidden nodes and it will have M examples. So now this P in blue shaded indexing is showing you number of nodes, and the one shown over here are number of examples. So now you can observe from these matrices how we are actually implementing all these one-dimensional equations by vectorizing them into this form and then to this form. And this can be easily implemented by using matrix vector multiplications. That's why we want to do vectorization of these codes. Okay, so the second equation, the first equation is this one, as we have discussed. This is the first equation. The second equation for this is this one. This is the second equation. So this is also quite evident from what you are seeing here. It's easy to understand. I guess there is no point in discussing this one because it will also have the same dimension as that of Z. And the reason for that is because you are actually running a non-linearity on it, and non-linearity doesn't have any dimension. So that's why whatever dimension you will have for Z, the same dimension will be for A. Okay. So now from now onwards, what I will do is it's a slight hack that I am doing, and what is that? I just want to remove this symbol and keep it as A for simplicity. But you can keep in your mind that if I am writing this A means actually I am actually writing this A, and this bold A is different. So just to avoid the confusion, I am writing it as A. So you have to keep in mind that from now onwards, whenever I write this capital A means this one. And same for this W also, because it's very difficult to write this every time like this. So just to avoid that confusion, I am writing it as W now. But this W and sorry, this W and this one is different, and this is also different. So uh, just keep this in mind. So when I am saying capital W, that means I am telling this one and not this one. Okay. So if that is the case, then what we can do is we can represent this complete neural network which is given over here, which has different weights connections given over here. This one is the weight. This is the weights for node 2. This is the no weights for node P. So what you can do is you can completely represent this particular weight matrix which is given over here for layer 1 as W1 and B1 with a single matrix. So now what we are doing is we are actually completely representing this using these two equations which are given over here. So the first equation is Z1, which is W1 x plus B, and same A1 as sigma times Z1. And please note that this earlier we had this one, but now we have replaced it by A. And same with W also, and somewhat same with Z also. This Z is also now changed because earlier it was in the fashion like this. I have removed it and changed it to this Z. And this bias B also is also changed. So you have to keep this in mind that whatever I am writing here to represent this equation involves double vectorization. It's not at the lower level of the lower level of the because this is the lowest level. This is the lowest level, and this is middle level, and this is the highest level. So what I am telling is I am writing the highest level only, not the lowest one or the middle one. So if that is the case, then you can represent using this equation this complete uh, single layer neural network, and again you can write it in this fashion also as given over here. So what it says is you have a matrix X, you are passing it to the passing it to this this is a big node which involves each and every individual nodes of a hidden layer, and it takes two inputs, one is the three inputs, one is the bias, this is the weights and X, and it outputs A. So this is nothing but a implementation of these two equations. So now once you have this, it will be easy for us to do multiple things which we'll be seeing in our next slides. Okay, so this finishes off with the uh, model where we have single layer, like this is the single hidden layer with P nodes. So this finishes off with the analysis related to that. So if anyone has any questions here, I can address it. Otherwise, we can move
Uh,
forward.
Sir,
Yeah.
in the dimension of the bias matrix, it is P cross M. So are we
Okay.
taking different bias for every example, or would the all the columns be same?
Column. See, the thing is, we will replicate it actually. The biases are, where you are saying this one you are saying, right?
Yes, yes.
So this one will be, this will be replicated same. This will be, so it will be different. But for a particular layer, when you will do implementation in TensorFlow, it will be replicated. So it will be like mostly it will be same.
Okay, okay.
Yeah. But it will change during the back propagation when you will do that. So we will discuss that also. Okay, so one thing is like now we have this hidden layer with P nodes. So now we will see the motivation for multiple layers. So as you can see, this is the single layer. So let's see what is the motivation, why we have to move from this single layer hidden to multiple layers. What is the point in doing that? So we will address this motivation of using multiple layers using two different point of views. The first is the regression point of view. The second is the classification point of view. So based on that, we will see whether there is a need for multi-layer or not. Or can we do it through single layer? If it is, then what's the point of using multiple layers? So the first point that I want to discuss is the regression point of view. So in the regression point of view, what we have is, let us say we have this complex function fx which has to be realized. And this fx is 2 sine x square plus under root of 5x. So this is and this corresponds to that. So it's a plot which actually is plotting this particular function fx. And now what you have to do is, you have to ask yourself, can a single layer perceptron solve this problem? So any idea whether a single layer perceptron can solve this problem or not? Can anybody tell, uh, is it possible by a single layer perceptron to solve this? Okay, so the thing is, as you can recall, that a perceptron is basically a single layer perceptron is implementing z is equal to wx plus b. So it's a sort of a straight line that you are implementing. So if that is the case, what will happen is you will actually try to fit a straight line like this, or maybe any other slope. It depends on your fitting, and it's not necessary that it should pass from zero. It can come from here also. So all these different variants of straight line will be implemented by perceptron. But as you can see that this particular curve has a lot of non-linearities, and whatever, let us take this particular equation, then you observe that,
Sir,
yeah.
there is some pop-up on the screen for a
Oh,
moment.
okay, I'm sorry. Okay, now it's okay.
Yes, sir.
Okay, so as you can see, I'm focusing on this particular line. So if you see the errors that is made by all these points, if you take these points as a sampled version of this uh, thing, then what you can see is the errors that it is making on these lines. So if you make a 90-degree, projection on these y is equal to whatever line it is, so you can see the amount of error it is incurring here. So this is not desirable because this particular line, as you can see, is not a proper fit to this line, this equation. So this, because of this problem, we had to, think like, is it like whether the single layer perceptron is really worth or not. So based on this, we have a motivation that can we try to use multiple layers in our neural network? Will it solve our problem? So let's see that. So now what I have done is I have represented this equation. As you can see, we have actually three inputs. One is x, one is y, another one is 2. So what I am doing is I am representing this using this graph. So you can see you have three inputs. One is x, another one is y, and the third one is 2. So this is acting as your input layer. So now what I am doing is I am actually multiplying x with 5 to get a, so this is basically a node which is actually, multiplying these two inputs together and giving you a value of 5x. So why we need 5x? Because you see here we have 5x as the one of the components of this equation, and then it has to be square rooted. So let's pass this through a hidden node which implements a square root function. So what will happen is here we will get square root of 5x. Okay, in the second case what we want is x square. So that's why I am passing this particular input into this particular node which is actually implementing a square function. So what we will be getting is as a x square here, and then it is operated on sine function. So once you multiply it with sine, you will get sine of x square, and and this sine of x square will be again multiplied by 2. So this is a multiplication operator. So this particular node is actually implementing that function. So what you get is 2 sine of x square, and then you finally implement a addition operator. So this particular node is actually implementing addition operator, and then you will get the final function fx. So this we call as a computational flow diagram, which we will go in details in our next lecture when we will discuss back propagation. But this is what we call as computational flow diagram, and by that what we mean is how the computation is flowing. But keeping this term aside for back propagation concepts, which we will do in later, in our next week course. But for now, what you observe from here is that what we are doing is we are actually somehow representing this particular flow in a form of a neural network, where this is your input feature space, this is your second hidden layer, oh sorry, this is the first hidden layer, you can say like that. This is a second hidden layer of a neural network, this is the third one, and this is the fourth. So some way or the other you can think like this way. So as a result of which you can observe that there is a strong need of having multiple layers. Earlier we had only this layer. So because of this reason, you can observe that we have to have a multiple layer in order to solve real practical problems. Otherwise, you cannot solve multiple layer problems using single layer perceptron. And some way or the other, it is actually, there is a theorem in machine learning which is called as universal approximation theorem. So what it says is that the neural network which you are trying to use, it will try to actually fit the curve, whatever curve it is, how whatever complex curve it will be, the neural network will be able to fit that. So that's why it is called as a universal approximation theorem for neural networks. So they have shown that neural networks can do a very good approximation of any of the function that you will give it to it. So, so this is one of the main reasons we, from a regression point of view, that we are moving to multiple layers instead of having a single layer. The second point of view, that as you know that in machine learning we have 2 point of views. One is classification problems, another one is regression problems, which are in majority. There are other problems also, but for this particular case, we are considering these two. So, in classification point of view, let us see another challenging problem, which is a XOR problem. So, the one of the important thing is, can a single layer perceptron solve this problem or not? So let us see what is XOR in terms of the truth table. The XOR in terms of the truth table is that if you have odd number of ones, then your output will be 1. So here you see, if you have 0 0, output is 0. Here you have odd number of ones, output is 1. Same goes with this. Here it is even number of ones, so output is 0. So this is our truth table. So now what we do is we will plot this diagram, we will plot this truth table onto the feature space, where the first feature is x1i, the second one is the x2i. So this is the feature space for this particular truth table. So now the important thing is, as you can see the scattering of the plots, when you plot the data, there is a problem. And the problem is you have two data on this side like this, and two data are on this side. So how to separate it? Using a single layer perceptron. And the reason is, as you can see, the single layer perceptron is actually implementing a line, as I am telling you so many times, like z is equal to w transpose x plus b. So what you will do is, this perceptron will always solve a straight line. So can you separate these points using a straight line? It's not possible, because you can draw a straight line like this, let us say. So in that case, what will happen? In that case, this 0 is coming as an outlier, because when you are separating 0 from crosshairs, and if you are taking this as your line, this is the outlier. And if you do the other way around, let us say if you do like this, then what will be the outlier? Outlier will be this one, because because we know that perceptron cannot separate the perceptron always implements a straight line. So that is the problem. You cannot solve this problem using single layer perceptron. So what you need to have is, you need to have something like this, some boundary like this, a non-linear boundary which can separate zeros from 1. So this is a non-linear boundary, it's not a linear boundary. So because of this, which is the classification point of view, we have to take help of multiple layers perceptron. Without multiple layer perceptrons, you cannot do that. And again, you can see this is the neural network corresponding to it. And I leave it to you to solve it, like what will be the W's and the B's for all this. If you are interested, you can do that. So if you calculate all these W's and B's, and we have now this and this. So this is actually some way or the other you are implementing. Now it's a two layers. So this actually gives you y hat, and this motivates us to look for, you know, this motivates us to look for, using multiple layers instead of using single layer. So now we have discussed enough as the reasons to go for multiple layers. So let's discuss the capacity of these multiple layers as we have discussed earlier also for the case of single layer. So as you will have, multiple layers involved, then you can see that all these hidden layers which were here, these are the hidden layers, right? So this hidden layer is actually implementing this, and this hidden layer is actually implementing this, and this we have already discussed as an individual in our earlier slide, where we were focusing on single hidden layer, single output, single hidden node. So this we have already discussed, and this we have already discussed. So but summing of this and getting the output here for two different hidden layers will give you a complex function which is given like this. So you can see how these two are actually combined and are giving you a complex function which is given over here. And you can see here you have a bump. So this bump is in the middle. So this only can be realized if you do this type of architecture. So this is basically the capacity of the layers when you are in 3D flow. So here it's a 3D plot for that. So now again this is again showing you that something like this which actually advocates using the multiple layers and multiple hidden nodes. So here also you can see if your R2 had these points, and R1 is having only R1 is having these points, and R2 having these zeros, and some way or the other in R1 here this is the region where you have crosses. So now you can see how this neural network can actually separate these classes. So it is inherently implementing some complex function which a single node perceptron cannot do. So, so that's why we have to look for multiple layers in this and multiple nodes in these neural networks. Okay. Another motivation is from biological inspiration. So as you can see here, we have a human brain. So last time also I have discussed that here in this particular node you are seeing this side, it's actually detecting the features which are very small features, and the features are edges. These edges you are actually getting here in this particular node, and then they have another node which takes these features, the lower level features edges, and convert it into high level features which are nose, mouth and eyes, and then it propagates further here in V4, and here also you can see now at this level the features become more complex and it detects face. So this motivates us from biological point of view also, that in our brain also we have multiple nodes which are cascaded, multiple layers which are cascaded, and each of these layers will be implementing some complex functions. This is again showing you that same thing, like how we are doing it for multiple layers. Okay, so now the thing is, now what I am doing is I am taking this two layers. This is the first layer, this is the second layer, and this is the block, this is the diagram for it, and you can see how I am writing the weights here for each of these individual. This convention I have already discussed now, but for the uh, second layer, the met this will change. As you can see now it's indexing with 2. Why it is changed? Because we are not on the second layer, that's why it is 2 now. So in order to simplify this, what I am doing is I am representing all these weights which are given over here as W1 B1, as we have discussed earlier also. And for these weights, whatever weights you have in this blue cloud, will be represented as W2 V2. And now we are considering P hidden nodes, and here we are considering Q hidden nodes. So we have generalized it. It depends whether P is 2 or 3 or Q is 2 or 3 or whatever. So it's a generalized complete neural network. You can extend it further to 3 layers, 4 layers, whatever. So the computational graph for this particular thing, as you can see here, the computational graph for this particular network will be represented like this. This is the computational diagram. So this was for the first layer, and this is now for the second layer. So now you are cascading the two, and you see we have in this case input as X, and it takes W1 and B1 like this, and then whatever computation you are getting here in the form of A1 is actually feeded it into the node here with W2 and B2. So I think okay. So the thing is, you have to be comfortable with all these conventions, because as we move forward in the lectures, we will be making use of all these definitions and parameters, and at that time it will be difficult for me to come back to this. So it's better for you people to get used to it to in this week itself, because next week we will be going in more details using back propagation. So so the thing is, now for this forward propagation, for this particular thing, why we are calling it as forward propagation? Because the data is flowing from this side to this side. That's why we are calling it as forward propagation. So now we will be writing the equations governing this particular computational graph, and it's very easy, as you can see, it's very easy. Like this all we have already discussed. This two equations we have already discussed, and here you note one thing which is important. Now it's P nodes. Earlier it was 1, 2, 3, 4, whatever we used to take for the number of nodes in the first hidden layer. Now it is P nodes here, and you can verify the matrix dimension multiplication, which is important whenever you do anything, because if the matrix dimensions doesn't verify, then this means there is a problem in your implementation and even in the derivations. Whenever you do some derivations in your later higher level courses or whatever, the equations have to be satisfied in terms of the matrix dimension. So same thing for here, for this one. Now the important thing is, you can write the same equation for the second node, which is given over here. But now the input is A1. So if the input is A1, so instead of X, which is given over here, you are writing A1 here. And again, same thing will follow like the one which we had earlier. But now this is Q, as you can see, because in the second layer we are taking Q output nodes. That's why it is Q now. So this represents the forward propagation for this computational flow diagram, and make yourself comfortable with all these equations, because these equations we will use when we will back propagate and understand the back propagation in this neural network. Okay. So once we have a small picture, I just wanted to give you a motivation of what's coming in our next lecture. So once we have completely understood this particular part, so this we have completely understood, right? So these nodes can vary as many as nodes you want. You can represent it using these circles. So once we have understood this, now the important part is what you are doing is you are actually representing this A2, as we have discussed earlier also, that this A2 is not nothing but A1 to AQ, and these A1 AQ, please note it's bold A's. So you can go back to the matrices and you can see there. So these A1 to AQs are bold AQs. So, so these are the results of the output that you will get from the output of this node, and we are taking as 2 because we are taking output at the second node. And what we have is the actual labels that you will already have for the supervised learning. So these nodes will this value of this y is already known to you. So what you do now is to take the difference between this y and the activation outputs which are given over here due to the neural network. And this loss function that we will define later is basically taking the difference between y and the a's. So these two vectors will be taken as a difference of that, and this will be fed into the loss function, and the loss function value will be calculated here. So for classification, you have actually Q classes. That's why we have these nodes. So if you take a binary class of Q equal to 2, then you have two output nodes, and the dimension of A2 will then be 2 cross M, which is given over here. And one thing to note is that since we are using sigmoids here, like at the output, since we are using sigmoids, and sigmoids have a range of 0 to 1, that means you are actually calculating the probabilities. So if that is the case, then all these variables, which these are the random variables which are generated by the output layer, are actually representing the probabilities. So what we can do is we can write for at least for two variables we can write a12, and another one will have 1 minus a12. The same for the y's. So maybe in your earlier classes of machine learning, when you have went to the for your earlier course in machine learning, must have seen this type of loss. Maybe we will discuss this if some of the people don't know it. But this is the loss which we call as multi-class cross entropy loss. So this is actually running from I1 to Q, as Q is the total number of classes here. We have Q classes here, right? So this is actually that Q, and this is your yi log ai2. So this is the estimate value that is coming through the neural network, and this is the actual label corresponding actual value actually. This is the actual value and this is the estimated value. So what you are doing is you are taking yi log of ai, and this is what we call as a multiple class cross entropy loss. So for q is equal to 2, what you do is you write I equal to running from 1 to 2 for this particular thing, and then you can expand it and you can substitute. You will get these values. What you are doing, you are putting y2 as 1 minus yi, for a2 as 1 minus a2. So this is the loss function that we are defining here, which is the generalized loss for multiple class entropy, but for two classes you can take it as this one, and it's also called as binary cross entropy. So this is what we are having here. Okay, so one thing that I just wanted to show you is, maybe you guys must have seen this. This is the website for playing around with the TensorFlow, for the neural network. I can show you that. Can you see it? Students, can you see this website?
Yes, sir. Yes, sir.
So as you can see, this thing, maybe you must have seen this or not, I don't know, but this is the API that TensorFlow people have created. Here you can play around with all these neurons, like all the neurons or hidden neurons. So here we have this single hidden layer, so you can increase it to multiple layers like this. So you will have multiple layers at the in between the output and the input, and you can try to learn more feature engineering by using x1 x2 only as the input, or x1 square x2 square x1 x2. So it depends whether you want to use all these features along with that or not. So depending upon your interest, choice of interest, you can take whatever feature you want to, depending upon the problem. So for example, if you have this particular data set which is shown over here, you can immediately realize that taking x1 and x2 will not do the job, because this has a non-linear boundary. So either you have to take one feature which is x1 square to further, x1 square and x2 square to further enhance the classification accuracy of this particular plot. So you can play around with this. And regarding the training test data sets, which we will discuss later on, but I think most of you guys also knowing it, but we will be going in more details into what training and testing cross validation is, how we can analyze it. That's a different part, but you can play around with the training data set, noise, batch size, learning rate, activation functions, regularization you want or not, what is the rate, and what kind of classification you want. So you can play around with this API and can run this particular particular code, and you can see what kind of results you are obtaining. And that's it for today. And if you have any questions related to this lecture, kindly let me know. And one thing that I want to tell you is, like, you have to be comfortable with what I am showing here, because this will play a strong hold, when we will discuss back propagation. So I request you guys to, work around, write it on paper, and practice it. So any questions related to the discussion today that we have here? Okay, then fine. So today's lecture is over, and we will meet next week.
Sir,
Yeah.
will there be lab on Saturday?
Yes, it will be there. Lab will be there. So labs will always be there now from now onwards. Yeah. Okay.
Sir,
Yeah.
can you please share the lecture notes that you are showing us, and like along with the YouTube lecture videos that you are sharing on the classroom?
See, the thing is, I can share with you people, but the problem is, once I have uploaded the videos, I guess you can write from there, and at least you will have a practice of doing it. Otherwise, I would have done it. There is no problem in that. But if I'll share with you the lectures also, you won't write. So the videos are only shared because of the reason that you will write from there and understand what concepts is going on. Okay?
Yeah. Okay, sir. No problem.
Any other question? Okay, fine. So today's class is over. You guys can leave, and next week we will meet.